my research is devoted to normal subgroups of iterated Vria's product of permutational groups, and its some its subgroups, which is also permutational products. First of all, I say that I continue my research published in 2009 year. It was only start of this research. It was also Vria's product of two groups and the normal subgroups. I call in this research invariant subgroups. It was published in a physical mathematical journal. Is this journal paper calls invariant structure of Vria's product of symmetric groups. Науковий часопис of science of National Pedagogical University. It was in Ukrainian, but you can find it. You can find it by my name. And now I continue this research and make some correction because some isomorphic embeddings of normal subgroups I count as one group in this research. Now I make correction and continue this research. First of all, what is permutational Vria's product? It's a semi-direct product of two groups H and direct power of G in power X. X is a set on which H acting, on which H acts, and this acts by respectively permutation of the direct factors. This is type of inner Vria's product. It can be written by formula, by this formula, where B is base group of Vria's product, named by W, and H is top group of Vria's product. Also, the base group is direct power of bottom group G, so it's G in power K. Here H acts only by permutation of copies of bottom group, so it's not a whole automorphism group as in semi-direct product has its partial case, special partial case. In general, form elements of Vria's product can be presented as permutation of copies of tuple with copies of elements of base group with a permutation on which acting permutation from the top group. There is sigma from the top group and G1, G2, Gk is K copies of the bottom group. Also, it calls states of automorphism in the vertices. If we use presentation of group automorphism of regular rooted tree, it corresponds to the states of automorphism in the corresponding vertices, which also calls states of automorphism G in vertices. Rules of multiplication with the right action of group is the following. We see the first cortege of automorphism of permutations from cortege G is taken in the same order, and the indexes of second cortege is permuted by action of by right action of sigma G of element of top element of first group of first multiplier. Yes, and the action. What's the action? Action of H in general case H of is a subgroup of group permutation of the degree K. It's this group acts on the direct power of G and permutes copies of this group according to the permutation which acting. For example, we have two permutations and right actions of S4, which permute the permutation of bottom group according to the top permutation. We see this action. So it's such homomorphism in group of automorphism, but not whole automorphism, only automorphism from permutations. So once again, I recall that I continue my research, and more wide new research was published in Archive 3 years ago, but it is also older research, about 40 pages, and now in more general definition, in a more general of wreath product, the permutation of wreath product of H and G, here's action is right, is semi-direct product where G acts on direct power of H and with respective permutation of direct factors. For instance, it could be CP, like in C-low P subgroup, acting on copies of next group, bottom group, which is CP2. It's construction of C-low P subgroup of various product of permutational groups. We can present various product as group of automorphism of regular rooted tree, and the following isomorphism holds. This presentation is useful because we can use portrait of automorphism and state of automorphism in vertices. State in this vertex automorphism is restriction of this automorphism, but not only restriction, this restriction admits following decomposition. All automorphism can be decomposed on automorphism in these vertices, and it's continuous on this part of tree. This part of tree. I will write it next time. What is state of automorphism? Значит, we have the third presentation of various product by the Kaluzhnin table, which corresponds to infinite sequence of permutations group. This sequence acts on the direct power of sets xy, where xi corresponds to each group gi acting on this set. The Kaluzhnin table is the following, has following form, where G1 element of first group of permutation, X1 element from the first set of permutation on which acting G1, and G2 from X1 is function from this set to second group, to the second group, to the tuple of the second groups, and it corresponds to one of this group. Where G1 is written here is a function from such Cartesian product in Gi. The action is the following, determined by the following rule, and we denote the infinite Fourier product by W, or W with subindex infinity. Also, I introduce in one of my paper the L level subgroup and denote it by GK from L, a subgroup generated by all possible vertex permutation of this level. This subgroup isomorphic to the L coordinate subgroup of Kaluzhnin table, which considered first time by Vitaly Suchansky in 1990 year. But I use level subgroup because I use a presentation by portraits of automorphism and states of automorphism. So it's two isomorphic subgroup. And I propose to consider sub-Fourier product construction, which is semi-direct product too. But since it subgroup of Fourier product, where G acts on subdirect product by respective the permutation of subdirect factors, so it's not subdirect product in general sense, it's partial case. So I in my work I denoted by sub Fourier product with two sign of Fourier product. What is subdirect product? It was introduced by Birkhoff Garrett in the following work. It's such a subgroup of direct product with special condition which admits projection on each coordinate. The condition can be followed. Consider the normal subgroup of wreath product of two additive subgroups. For example, it's not permutation group, but it's additive subgroup by modulo P, and we can present it by such a table where P from ZP acts by shifts by modulo P, and AI from the bottom group. This subgroup has following cortege following tuple A1 AK, which satisfies the condition of this congruence that sum of elements, sum of residua by modulo P congruent to G by modulo P. And we have P different subgroups correspond to different G, for different rests by modulo P. This condition determines subwreath product. Subwreath because it's subdirect product. It's not direct product of ZP. It's a subdirect product which satisfies this congruence. So I shortly calls it subwreath product. The subwreath product firstly introduced by me, but it appeared in different works. In partial, in works about pronormal subgroups of Maslova and Danilo Olegovich Revin on the pronormality of subgroup of odd index in some direct products of finite groups, Journal of Algebra, and these applications. Also, it was appeared in my work. In my work about seal of two subgroups of alternating group, of alternating two subgroup, it was it has quite a rather structure in case from another P, which is not even number, but in case which if P equal to 2, it's not a wreath product, it's semi-direct product with such a structure. But this semi-direct product is exactly semi-direct product with of wreath product with sub-direct product, so I can call it sub-wreath product too. Why here is subdirect product? Because alternative group have to act by only by even permutations. So I cannot take arbitrary permutation on last level. On last level, it admits only half of permutations, exactly even permutation, even number of transpositions. So we have 2 in power k minus 1 and minus 1 because it's divided by 2, number of such tuples divided by 2 because of we use only it admits only even permutations. This group denoted by wk minus 1, and this is the same subwreath product. So it's it was in my work this construction too, but now I give it a new name for this construction. Now we consider the normal subgroups of two iterated wreath product. This subgroup satisfies the following condition, which have permutation on the first tuple of Kaluzhnin table, such which satisfy the following condition: this sum of decrements of this permutation is even number. What is decrements was described in a book of Sachkov about methods of discrete mathematics and its applications. It's equal to minimal number of transposition on which this permutation can be decomposed. But in origin, but its conclusion, original definition is such. it's a number n minus k, whereas k is number of cycles in cyclic decomposition of permutation p, and n number is a number which is degree of this permutation. For example, this number n, here is n, concrete number in we take a decomposition in cyclic, and we see how many transpositions, how many cycles there in the, and n cycle can be decomposed in n minus one transposition. So if it has k cycles, it can be decomposed in n minus k transpositions. So it's characterized in our case the parity of permutation. And this group I call generalized alternative group of first level. First level if we numerate from the zero. If we numerate levels and multipliers of Brias product and the part of Kaluzhnin table from zero, because it's a natural number of components in this table. And in power 1, we have n permutation, and in power 0, we have 1 permutation. So it's useful numeration. Okay. Значит, we can spread the previous definition on 3 multiple Brias product by recursive way. We take previous group A tilde 1 n, which acts on tuple n. You see lower index n. It means it's x on n points. And here we use Brias product with A tilde 1 n. This group be denoted A tilde 2 n. A tilde 2 n, because on second level it has n tuples with n elements. Each tuple have satisfies the condition 1 from the previous slide. Satisfies the condition of parity 1. So we have n such tuples. The structure of this group is the following: A tilde 1 n is isomorphic to the subdirect product of direct product of n on direct product of n minus 1 copy of C2 and in case of permutational group of power 3, we have such semi-direct product. Okay, I recall that monolith of group is unique and minimal normal subgroup, which is not trivial. And group which has monolith calls monolithic. Also, it is isomorphic to intersection of all normal subgroup. In case it's non-trivial, such group calls monolithic. The following theorem about monolith of various product of permutational groups, and it states that it's monolithical group. The monolith of this group is our A tilde 1 n group. Group introduced in definition 1, A tilde 1 n O, this various product. I'm sorry. Monolith is without tilde. Here is tilde, but it's without tilde. Is Brias product E with AN, with alternated group. This group contains in this, but here is without one. It's another, quite another group. Here is a little incorrect without this index. Okay, the next definition of A tilde 2 n square. This is subgroup which has permutation on second level, which form even permutation on the second level. This it means that permutation of second level satisfies the following equality, and on previous level this group has trivial permutation. So it's group of depth 2. Depth is minimal level where is non-trivial permutation appear. The subgroup be denoted by A tilde 2 n square, A tilde 2 n square, and the subgroup defined in recursive way, E wreath product with A tilde 1 n be denoted A tilde 2 n, and this subgroup is subgroup of previous subgroup. Furthermore, E sub-wreath product tilde 2n is normal subgroup of three multiple wreath product, and the order of this subgroup is the following: n factorial in power 3n divided on 8. And now I recall the notion of normal rank because it's characterized the subgroup by its structure and on subject of prime or not prime. Yes. The group G is said to have finite normal rank R if R is smallest number with property that the finite set of elements G1, G2, Gn of the group G, that arbitrary any finite set of n elements of group G, the elements there are elements H1, H2, Hm of H such that M less or equal to R, and the following equality holds: the normal closure On equal to normal closure of these M elements. This M no greater than R. No greater, less or equal to R. It means that R elements be enough to generate normal closure, which contains normal closure of any n elements of group G. Firstly, it was introduced in works of Kurdachenko, as I read, but I find it in the Journal of Algebra Discrete Mathematics in works of Olga Yurina Dashkova. The following statement: the normal rank of generalized alternative subgroup of first level is equal to n minus 1. The sketch of proof is the following: we use generators. We use n minus 1 generators. T tilde 1 is generators is which presented by table of Kaluzhnin in the following form. It's when n is odd. When is odd, so it's coprime with 2. It's coprime with 2. It's first case. It means when I exponent it to power 2, I got a trivial element on second coordinate and on last coordinate. And in this coordinate, n cycle become to be another n cycle, but sure it will be n cycle. It's not decomposed on more little cycles because n coprime with 2. So we know theorem about generators of Sn. Arbitrary element can be generated by pair long cycle n, cycle of length n, where n is odd, and the transposition one of elements 1, 2. And the second element t tilde 2, I permute elements on first and second coordinate. So on first coordinate be transposition, and on second coordinate be n cycle. Yes, and I use the another rising to another power n, which become first element first transposition left to be transposition because power is odd. For example, this transposition in power 3, this left to be this transposition. But this element in power n became to be trivial. And after it, I will multiply table T1 tilde on table T2 tilde. It multiplies directly. And I, in such way, I can generate arbitrary element on the first coordinate. Thus, any questions on this stage? Okay, in second case, when n is even, in this case, I use another pair of generators of Sn is A and B. You can see it's transposition and n-1 cycle from 2 to n. And in this case, the GCD of n-1 and 2 is 1, and I use the following permutation to construct the two generators, which in similar way can generate arbitrary element of Sn on first n-1 coordinate, but in last coordinate I put transposition to get an even permutation in product. If I in the product of all permutation of this tuple, to is this satisfy condition 1 from definition 1 of parity? Does any question to this idea of this proof? Okay. The following theorem about structure of proper normal subgroups of two multiple
presentation. So I have like 20 minutes. We'll get there. In the minute, don't. I have to.
What's the question again, please? What's the question? Okay. Such Fourier's product has 8 proper normal subgroup, which can be divided on 2 series. First series has depth 1, and second series has depth 0. And this subgroup, Sn Fourier's product with tilde Am, has 2 isomorphic copies embedded in different ways, in different ways. So this here is for subgroup 2. Here's for subgroup and here for subgroup, and the 2 subgroup which is trivial subgroup and whole subgroup, no proper subgroup. And in whole we have in total we have 10 subgroups. The structure of subgroup Sn Fourier's product of Am tilde is the following, where subdirect product satisfy the condition 1, which was on second slide, and which was presented above. And in terms of the semi-direct product, this subgroup has the following structure. Also, this subgroup, I will do these 2 copies of subgroup. I will denote A tilde n 1 and B tilde 1n. Yeah, and it corresponds in gap system to groups of order 648 with identificators 733 and 704. It's even 2 different identificators in the algebraic packet.
All right.
The commutator of this subgroup is isomorphic to the Fourier's product of alternative group power n and A tilde M1 with index 1. Somebody have question or some noise? I can hear some noise. Please.
Yes, I think Dr. Timmy Tom, I think have question.
But I don't hear this question. His question. Okay, the next subgroup T tilde 1n is subgroups which consist of element of 2 classes. First class has only even permutation on the first part of collusion table, and the second class of elements have only odd permutations on the first tuple of the collusion table. So first class is isomorphic to subgroup Ivrias product An, where An is alternative group, which consists of even permutations, yes. And this class forms subgroup. Second class sure do not form subgroup, but together they form subgroup Tn with tilde. This I call generalized diagonal group of level, because the diagonal group has the same elements on the tuple, but this element subgroup have elements with the same parity on the level. Yeah, the structure of this subgroup in case of n equals 3 is the following semi-direct product. In general case, the following semi-direct product. The following proposition holds: a subgroup T tilde n is normal is two multiple Vrias product for n equal or greater than 3, equal or greater than 3. Elements of first type form subgroup E Vrias product An, and subgroup E Vrias product An is the monolith of the Vrias product of symmetric group of degree n with symmetric group of degree n. The subgroup Tn tilde has a structure. The following definition. In the three multiple Vrias product, we define the T tilde n square as subgroup which consists of the following class of elements. First class of elements belongs to this subgroup, is whole subgroup. E Vrias product E, Vrias product with alternative group of degree n, and the second class of elements presented by collusion tables with depth 2, where on second tuple of collusion table are placed permutation which are odd, only odd permutation. So these two classes forms a new subgroup T tilde n square, and this subgroup is normal in three multiple Vrias product of Sn and have the following structure, where this square plus in square means subdirect product defined in previous definition. Here. It means that all permutation have the same parity. Do you understand it? Okay. Now I present the lattice of normal subgroups of two multiple Vrias product for the case of n is odd. N is odd. The case n, you can see n congruent to 1 by modulo 2. First whole subgroup, then here two subgroup which has two isomorphic embeddings in this group with index 703, 704, yes, and group with the same order but with another structure presented by Vrias product alternative group on symmetric group of degree n, yes. And the following subgroups embedded in these groups. In total, 10 subgroups with non-proper subgroups. The structure of lattice subgroup for the even n presented on the following diagram. We can see that T tilde n includes in the subgroup which we denote R tilde 1n. It's so because of number of permutation is even, and it's and the general parity of level in this case is even, because if all permutations is odd but the number of is even of such permutation, Is this result is checked by gap system and proved analytical too, and has an analytical justification too. In case n equal 4, we got a new normal subgroup, which is Klein subgroup, and we obtain 11 normal subgroup. New subgroups is the following. New subgroups is the following. 11 is only proper subgroups. 11. So we have 8 plus 3 new. We obtain 11 new normal proper subgroup. Okay, the structures in terms of semi-direct product are the following. H1 is isomorphic to the whole various product and has order 1296. We have 8 proper normal subgroups of this subgroup, and these subgroups presented above. H2 has 3 copy. Has 3 copy. 2 of them was described and have indexes 703 and 704. Yes, it's various product Sn with a tilde 1n. Yes, and the third is various product alternative group with symmetric group of degree n. They have the same order, but rather different commutator subgroup and many another different subgroups and structures, element of structure. And generalization on multiple various product. The set of elements of such multiple various product with depth k, satisfying the following condition of parity of decrement of this permutation forms the subgroup, and additionally we call a tilde k sub nk. It means it acts on n. It has n in power k permutations on level number k, and the whole tuple, only whole tuple of n power k permutations forms even permutation, only the whole tuple, but subblocks of length n or n square do not always form the even permutation. The following generalization of this definition admits blocks with the even permutation of length n. Here we have blocks of length m. You see here, if I going from 1 to mm, here is 1, here is n in power m. We have first even block, then next block of degree n in power m, and the sum of this block forms n in power k permutations of k level. This shows this subgroup is a normal subgroup, and the subgroup is belongs to the previous subgroup. It's is a subgroup of previous group. You see, this group have even block of length n in power k, but this subgroup have blocks of have n in power a minus m blocks of length n minus m. These blocks are even. Sure, it's a subgroup of this group, and the following normal series holds. The following a tilde k and k is normal subgroup in wk where WK is multiple wreath product of permutational group of degree n. And now we start to increase the degree of block and obtain the normal subgroup of this subgroup. And this decreasing going us to last subgroup, which is A tilde K n, which is also so normal. It's exactly normal series, not subnormal. It's exactly normal series. It means that this subgroup is normal in first subgroup in WK. All subgroups is normal in the first subgroup. It's a very strong condition.
Sorry, Dr. Ruslan. Still have 5 minutes off.
Okay, thank you. This series have the following factors, following quotients, and concept of, I will skip concept of normal saturation set. It's set which contain all normal subgroup. For example, diedral 2K saturated by C2K and 2K and DK. It means all normal subgroup or is a normal subgroup or cyclic subgroup of degree 2K or diedral group of DK. I can divide it on classes. Classes group which all normal subgroup belongs to, or class subgroup which denoted by A tilde E n sub n e. Yes, this subgroup was first in normal series, first proper subgroup. You've seen it. Another group are embedded is first class, and second class is T tilde nk. And now I present a theorem about mutual commutativity of all normal subgroups of WK. The structure of this structure of Sn wreath product An A tilde N1. This is a structure of this subgroup. If we take instead Sn An, we lost this C2, which induce the parity of permutation, automorphism of parity in permutation is in this group. Yeah, this group has a group of automorphism C2. Yeah, and this induced the parity acting giving this image 1 or 0. It means parity of permutation from C3. And we lost this. If we lost this, we get alternative group of power 3 sub-wreath product with generalized alternative group of third level, which has the following structure. Okay. I have presented the structures and the future research on topologies, which I only start to consider. We generalized on infinite wreath product and propose to consider the following open sets, where on class place we have generalized alternative group of class level, yes, of degree K, yes, and open all subgroups of this all normal subgroup of these groups, which is alternative group of lesser degree of this subgroup, will open subsets too. So we have the following open subsets, or alternative, we can use another topology which is analogous to the cylindric topology. Yes, and this open sets we can see the if we take U and V, which is subgroup of OK sub NK, and which subsets or subgroups is denoted subgroups WK, and multiply it. Yes, the blocks of parity, it will belongs to OK again, because the biggest block of even permutations of which form even permutation have degree k. It's easy to check the continuous of multiplication and the open sets of K's level permutation denoted by O, K, and NM, where n no greater than k. Base of each level subgroup has finite number of open subsets. Only finite number of open subsets. The number of all level subgroups is countable. Therefore, the countable Cartesian product of the topologized form forms the Tikhonov topology. As well known, every Tikhonov product of finite sets is homomorphic to the counter set. So now I try to strictly prove the following theorem that this topology group forms a space which homomorphic to the counter set. The one of ideas to consider the following quotient, yes, and obtain the following isomorphic subgroup. It's direct product of the two. Then this topological
your
group,
time is finished.
Okay.
Yes, your time is finished.
Okay, and the last theorem about three multiple product, it has 50 normal subgroups. It can be divided on these classes. You can see it and see I use recursive, and it's E subgroups of two multiple subgroups, two multiple wreath product. Here I present, I counted, and bn square is another embedding of a tilde n square under 2. It's easy to count by this. Thank you for your attention. Here's my list of literature. Maybe you have any questions.
Thank you so much. Yes, thank you so much, Dr. Ruslan, now for your nice presentation and great information.